So you're building an app, and you need to store a list of things. Simple enough, right? Well, not so fast. The way you choose to store that list can make or break your application's performance. It can be the difference between something that feels lightning fast and something that just grinds to a halt. Today, we're diving into one of the most fundamental choices in programming, the epic showdown between arrays and linked lists. Think about this for a second. What do you think is faster? Jumping straight to the 1,000th item in a huge list, or, say, inserting just 10 new items right up at the front? The answer, as you might guess, is it depends. And that dependency gets right to the heart of the trade-off between our two contenders. One is all about speed, and the other is all about flexibility.
Okay, let's get into it. It's time to introduce our contenders in this storage showdown.
In this corner, weighing in as the rigid, orderly champion of speedy access, we have the array. And in the other corner, the flexible, agile champion of easy changes, the linked list. You can see right away they're built for different things. One is a powerhouse, the other's an acrobat, and their strengths come from totally different designs.
So, what gives them these completely different personalities? Well, it all comes down to the nuts and bolts of how they're put together in your computer's memory.
You know, the best way to wrap your head around this is with a simple analogy. Think of an array as a perfectly organized bookshelf. All the books are right next to each other, in order. If you want the 100th book, you just go to the 100th spot. Boom, you're there. A linked list, that's more like a treasure map. Each item or clue holds its value, but it also points you to the location of the next clue. You can't just skip ahead. You have to follow the chain one clue at a time to get to the treasure.
And that bookshelf idea? That's exactly how it works in memory. It's called contiguous allocation, which is just a fancy way of saying everything is stored in one big continuous block. This is the array's secret weapon. Because everything's packed together, the computer can do some super simple math to find any element instantly. It knows where the list starts. It knows how big each item is, so it just calculates the exact address. No searching, no guessing, just pure speed.
The linked list, on the other hand, is completely different. Its elements, which we call nodes, can be scattered all over the place in memory. They're not neighbors at all. So how does it keep track? Well, each node holds its piece of data, but it also holds a pointer, basically the memory address of the next node in the sequence. It's a chain, and that means if you want to find the 100th element, you have to start at the very first one and follow 99 of those pointers to get there.
Okay, theory's one thing, but how do these two actually perform in the real world? Let's throw them into the gauntlet and see how they handle the most common operations. All right, this table tells you almost everything you need to know. Look at that first row, access by index. The array is a clear winner with O of 1, or constant time. That means it takes the same amount of time to get the first item as it does the millionth. It's incredible. But then, look at the next row, insert/delete at head. The tables are completely turned. The linked list is O of 1, super fast, while the array is O of n, which means it gets slower the bigger it gets. This right here is the fundamental trade-off.
This really is the array's knockout punch. O1 random access. Want the 5th element? Bam. The 5 millionth? Bam. Same exact time. It's why for anything that requires you to frequently jump around and read data by its position, the array is the undisputed king. No question. But don't count the linked list out. It's got a killer countermove. O of 1 edits at the beginning or end. Think about it. If you want to add a new item to the front of a linked list, you just create a new node and have it point to the old head. Easy. But in an array, oh man, you'd have to physically shift every single element down by one just to make room at the front. For a huge array, that is brutally slow.
Okay, here's a super important point, especially for you folks doing technical interviews. You'll hear people say linked lists have O of 1 insertion, but that comes with a giant asterisk. It's only O of 1 if you already have a pointer to the exact spot you want to insert. If you have to find that spot first by searching from the beginning, well, that search is O of n, so the whole operation is O of n. It's a classic gotcha question, so don't fall for it.
So you might be thinking, wait a minute, an array is a fixed block of memory. What happens when you run out of space? It seems like adding items to the end would be a huge problem. But modern arrays, or dynamic arrays, have a really clever trick up their sleeve.
Here's what happens. When the array gets full, it doesn't just give up. First, it finds a whole new, much larger chunk of memory, often twice the size. Then, it painstakingly copies every single element from the old array into the new one. Finally, it throws away the old, smaller array. Now, that copying step is definitely slow, right? It's an O of n operation. But, and this is the brilliant part,
because it doubles in size each time, these expensive copies happen less and less often. So if you average out the cost over thousands of editions, the average cost is still basically constant. We call this amortized O of 1, and it's what makes adding to the end of a dynamic array so fast in practice.
But wait, there's more. There's a hidden performance factor that you won't see in a standard Big O chart, and it's called cache locality. See, modern computer processors are incredibly smart. When you grab an item from an array, the CPU basically says, hey, you'll probably need the next few items too, and it prefetches them into its super-fast cache memory. This makes scanning through an array crazy fast. But with the linked list, because the nodes are scattered all over memory, the CPU can't predict what's next. This leads to a ton of cache misses, which can make a linked list feel much slower in the real world, even for operations that look the same on paper.
So, who's the winner? Well, after this whole showdown, the real answer is, it depends. There's no single best data structure. It's all about picking the right tool for the job.
So let's break it down. When should you reach for an array? You're going to want an array if you need fast random access. That is, jumping to any element by its index. Or if you need to iterate through every single element as quickly as possible, taking advantage of that sweet cache locality. And if you're mostly just adding items to the end of your list, the array is your champion. And when is a linked list the hero? You'll want a linked list if you're doing a ton of insertions or deletions right at the beginning of your sequence. It's also great if you need to insert or remove things from the middle, assuming you already have a pointer to that spot. Basically, if your list is constantly changing at its ends or in the middle, a linked list gives you that flexibility without huge memory operations.
All right, let's wrap this up. We're going to talk about the key points that will give you a real edge in a technical interview. This is how you go from just knowing the basics to really thinking like a pro.
So if you're in an interview, here are the high-signal things to say. First, when you talk about adding to an array, use the term amortized O of 1. It shows you know about resizing. Second, bring up cache locality. That proves you're thinking about how hardware actually works, not just theory. Third, when you talk about linked list insertion, make sure you clarify that O1 speed requires a pre-existing pointer. And a bonus pro tip, mention that in a language like Python, the built-in list is actually a dynamic array, not a linked list. These details are what will make you stand out.
And that brings us to our final question. We've seen that arrays are fast and linked lists are flexible. So what if you need both? How do you get the best of both worlds? The answer to that question? Well, that's where things get really interesting, and it opens the door to a whole new world of even more advanced data structures.